4.3 is the addition rule for handling situations where we're looking for the probability that on one trial, either A happens or B happens. Now, let me just make this very basic for a second. You told me that the probability, when you roll a fair die, the probability that it lands on 6 is 1/6. What's the probability that it lands on 1? 1/6. So what's the probability that it lands on a 1 or a 6?
2/6, 1/3.
Yes, yes. Took me a second. Yes, 2/6. You added those 1/6 plus 1/6 to get 2/6, and then you can reduce it to 1/3. But when you're looking for the probability of A or B, like landing on a 6 or a 1, you add those two probabilities together. You just have to be careful to not count anything twice. For example, if I'm talking about the number of people in here who have brown eyes and the number of people in here who have brown hair, then there would be some people that got counted twice because they had brown hair and brown eyes. When you're calculating probability, you have to make sure that nobody's getting counted twice. All right, that's the basis of 4.3. Have a little bit of terminology: disjoint or mutually exclusive. Events A and B are disjoint or mutually exclusive if they cannot happen at the same time. That means there's no overlap. In this Venn diagram, the red circle, this red circle is the probability of A. The yellow circle is the probability of B. There's no overlap between A and B in the second picture, so this would be a representation of two events that are disjoint or mutually exclusive. Here, where there's overlap, that's an example where the folks in this orange part are getting counted twice. That's an example of not disjoint. If you say everybody in the red and then count everybody in the yellow, those folks in the orange got counted in both groups. All right, so first let's just practice, is this joint or not disjoint? Disjoint or not disjoint? In a single trial, is it possible to randomly select a subject who is a Republican and at that same time that person be a Democrat? You can't be both. Now, you can vote split ticket, but that's a whole different issue. You have to register as Republican, Democrat, or other. So you can't be, one person can't be both a registered Republican and a registered Democrat. So does that mean those two events are disjoint or not disjoint? They're disjoint because they can't happen at the same time. Number 8, randomly selecting a fruit fly with red eyes and then finding out that that same fruit fly has dark brown eyes. Is that possible? One fly having red eyes and brown eyes? No, you can't have both. Now, don't make it harder than it is. Again, what about the fly that has one red eye and red? Yeah, stop it. This is plural. You can't have two red eyes and two dark brown eyes. So, disjoint or not disjoint? Disjoint. Number 10, randomly selecting someone treated with Lipitor and finding out that same person is in the control group and taking no medicine. Can that be the same person? No, it can't. So, joint or disjoint? Disjoint. And number 12, randomly selecting a college graduate and finding out, hey, that person's also homeless. That could happen. It's very unfortunate, very sad. But does that mean those two events are disjoint or not disjoint? Not disjoint, because it is possible for one person to be in both groups. There could be some overlap there. A complement of an event, new notations, very important. Whenever you see an A with a bar over it from now on, that is the complement of event A, and that's every situation where A doesn't occur, like rain and not rain. The probability of an event A plus the probability of its complement. If there are only two things that can happen, those two probabilities have to add to 1 because one of those two things is certain to happen. So from now on, if I just walk up to you in the hall and flash a flashcard A with a bar over it, you go, that's a complement. A and its complement are disjoint. That makes sense. They can't happen at the same time. Let's look at an example involving complements. From page 156, number 16 says 676 drivers were screened at a sobriety checkpoint and 6 were arrested for driving while intoxicated. In the A part, if I is the event of a screened driver being intoxicated, what's the value probability of I? Well, the probability of I is the same as probability of finding a driver who's intoxicated, and there were 6 intoxicated drivers out of 676. So that's very straightforward. The probability of a screen driver being intoxicated is 6 out of 676. And if you round that to 4 decimal places, it's 0.0089. The B part says, what does I complement represent? Well, if I is the event of being screened and found intoxicated, then the complement of I would be a screen driver not being intoxicated. Or I'm going to say being unintoxicated. Same thing. The C part says, what's the probability of I complement? There's 2 ways you can find that. One is to say if 6 out of the 676 were intoxicated, how many does that mean were not intoxicated? Just subtract and you get 670 out of 676 were not intoxicated, and you can enter that on the calculator, and it's pretty easy. However, it may be even easier since we already know the probability of a screen driver being intoxicated. How do you find the value of the complement of that? Remember that the probability of any event and its complement together, they have to equal 1. So if you know the probability of intoxicated, you can find the probability of not intoxicated by subtracting the 0.0089 that we already have from 1, and you get 0.9911. So the probability that a driver is intoxicated is less than 1%. The probability that a driver is not intoxicated is a little over 99%. And these two together, added together, give you 1 because the probability of any event plus the probability of its complement should give you 1. One other example I added to this page just because some people get stumped when you have a decimal within a percent. That shouldn't matter. To remove the percent sign, you still have to move the decimal 2 places to the left. The question is, if the probability of winning a certain casino game is 0.23%, what's the probability of not winning the game? Again, winning and not winning are complements of each other, so those two probabilities should add to 1. If I know the probability of winning is 0.23%, I have to write that as 0.0023 as a decimal. And the probability of not winning is 1 minus that decimal, or 0.9977. So the probability of winning is 0.0023. The probability of not winning is 0.9977. The formal addition rule says the probability of A or B is the probability of A, the probability of brown hair, for example, plus the probability of B, the probability of brown eyes, minus those folks that got counted twice. I don't memorize that like I memorize the quadratic formula in algebra. I just understand what that means and make sure to always remember to count the possible outcomes in a way that no outcome is counted twice, which is what the intuitive addition rule says. Find the total ways A can occur, the total ways B can occur, but find that total in a way that no outcome is counted more than once. And then when you get that total, you divide it by the total possible number of outcomes, and that gives you the probability of A or B. All right, here's the table. And I'm just going to tell you, you are going to love these tables or hate these tables. It's going to take a little bit of practice to understand how to read them, but tables are a good way of organizing information if you are able to read them correctly. For example, if I say this is results from experiments with polygraph instruments, if I say how many people had a positive result, what would you say? It's okay if you're wrong. I just want somebody to tell me a number. 42. If you say 42, then you're right. Those folks did have a positive result, but they're not the only folks who had a positive result. These 15 had a positive result also. So if I say how many had a positive result, that's a whole row. If I say how many had a negative result, that's a whole row. If I say how many actually were lying, that's a whole column. It's not just these 42, not just this 9, but 51 who were actually lying and 47 who were not lying. So for any number on that table, you have to tell me in which of two categories that number belongs. Was the person telling the truth or lying? And then what did the polygraph say, true or false? You have to tell me both of those things. If we're looking for the total number who did not lie, that would be these 47. If we were looking for the total number who did lie, it would be this 51. If I wanted the total number who tested positive, whether they were lying or not, it would be this 57. And if I wanted the total number who tested negative, whether they were lying or not, then that would be these 41. How many people in all took the polygraph test? When you say all, do you mean 57, 41, 51, 47?
No, 47.
Okay, several ways you can do it. Without looking at what I wrote out to the side, you could just add up the numbers here, or this would have to give you the same answer if you added the liars to the not liars. That would have to give you the same answer. Or if you added the positives plus the negatives, that would have to give you the same answer. So there are 98 people who took the polygraph. What does false positive mean? It means something just a little bit more specific than that, because false positive and false negative are both inaccurate readings. So you were half right there, but what's the other half? What's false positive mean? The positive would mean the polygraph said that you were lying, but the false part of that means they were telling the truth. So you wouldn't, you're getting wrongly accused when you get a false positive. What about a false negative? What does that mean?
Liars are getting away with it.
That's an easy way to say it. The test said negative, but the person was actually lying, so they are getting away with it. In court, which would be worse, a false positive or a false negative? Yeah, we really try in our justice system not to lock away people who are innocent. That is probably even worse than letting go somebody who's guilty. So this shows why polygraph tests are inadmissible in court. Here's a good question. What's the total number of people who got the wrong result? Which would be 24. 24 out of 98, about a quarter of the time, the polygraph was wrong. And that's why polygraphs are not admissible in court. They're not completely accurate. Not even, I'm going to say not very accurate at all. If it's wrong about 1 out of 4 times, that's pretty significant. All right, number 18 says, if one of the test subjects is randomly selected, find the probability that the subject did not lie. How many people did not lie? It's not just this 15. They were lying and they were not lying, but the test said they weren't. It's not just these 32. They were not lying. The test said they were. It's the total of this column. It's 47 who did not lie. So how do you find the probability that a subject did not lie? 47 over 98. And if you write that as a decimal to 3 decimal places, somebody punch that for me real quick. 0.480. Anybody second that? All right. About half the subjects were not lying. So the probability that you randomly draw out a subject who wasn't lying is almost a half. It's 0.48. If one of the subjects is randomly selected, what's the probability that the subject had a negative result or lied? All right, let me think about this for a second. I want the probability of negative or lied. The formal addition rule says I would have to find the probability for negatives and add the probability that I got a liar, liar, pants on fire. But then what? If I just add those 2 probabilities and do nothing else, why is that not going to be right? Well, I do have to divide, but something else. There were folks that got counted twice. If I just add those probabilities, what about negative and lied? Lied and negative. These 9 folks got counted twice because they were in this category, negative, and they were in that category, lied. So the formal addition rule, I'd have to subtract off the probability of those who were negative and lied. Subtract off the overlap. Now, I know there's a little bit faster way to do this, but I want you to understand both ways. All right, how many negatives? How many negatives total? This is the negative row. Adam, it's 41. Probability of negative is 41 over 98. What's the probability of randomly picking a liar? Liar, liar, pants on fire. That's these guys right here, 51. So the probability of picking someone who lied is 51 out of 98. But then how many folks got counted twice? 9. Well, no, just these 9 right here that were in the lied column and were also in the negative row. So I have to subtract off those 9. I don't have to enter those 3 fractions on the calculator because they already have a common denominator. When I add them, I know my denominator is going to be 98, and it's much faster to, in my head or on the calculator, punch 41 plus 51 is 92. 92 minus 9 is 83. So 83 out of 98 were either negative or lied. And what would that be to 3 decimal places? Someone, please? 0.998. Anybody second that? All opposed? Somebody get a different answer? Miss April, what'd you get? Actually, remember that number from last time. Punch it one more time. 83 divided by 98.847, you said, Miss April? There's, yeah. And what was after the 6? So the 6 would, so the 9 would cause the 6 to round up to 7. I say rounded 3 decimal places. That means I want you to have 3 decimal places in your answer. All right. We're going to practice these tables a lot. We're going to do a lot of problems. Hopefully, when I'm talking to you, it makes sense. But then when you get home and you look at it, you really have to think hard about, hey, probability of lying is not just one number, it's a whole column. And probability of negative is not just one number, it's a whole row. All right. Ooh, another table. So I have this one printed as well. Oh. This is a table that summarizes the results of one study of 1,205 people. I'm glad they gave me that number so I didn't have to add them all up, who were asked a survey question. Doesn't matter what the question was, we want to know how many were willing to respond and how many were unwilling to respond. A pharmaceutical company is interested in the opinions of the elderly because they're either on Medicare or soon will be on Medicare. We want to know the probability based on age that each age group would either respond or not respond. In number 28 specifically, we want the probability that someone is over 59 and responded. Nobody say anything for just a second. Stare at the table until God whispers to you. How many people were over 59 and responded? Go for it. I heard different answers. Over 59, that would be the same as 60 and over, right? So there are 251 senior citizens, basically, 251, and responded. That's this whole row. So how many are in both this column and that row? Just the 202. This 202 out of 1205 would be the probability that we're looking for. I'm not going to write that as a decimal. It'll allow us to go just a little bit faster. You know how to do that now. What's the probability that a person refused to respond or is over 59? Oh, you know what? On the previous example with the table, I said there's an easier way, and then I didn't say what the easier way was. Somebody who was thinking, oh, I found it faster than all of this, tell me what you did. Somebody always finds it faster than that. You could just add up the negatives and then add the 42 to it without adding the 9 again. Either you really added the 9 twice, so you have to subtract it off once, or you just don't add it twice to begin with. All right, this plus that would be probability, or that would be the number who were negative or lied. We can do the same thing here, save ourselves just a little bit of time on number 30. What's the probability that the selected person refused to respond or is over 59? What's the first thing we need to find out? Okay, how many people who refused? How do I get that number?
49.
Oh, yeah? Only 49 out of this 1,205 people? The whole bottom row.
59 years there.
Okay, but that's not the question I asked, though. I asked, you were reading correctly. I asked, what do we need to know? Somebody said the number that refused to respond. The number who refused to respond, well, all of those guys on the bottom row refused to respond. So I need to add those up real quickly. Is anybody ahead of me and already done that? You are helping me so much. Thank you. And I had a second on that, right? All right. So 156 refused to respond. How many were over 59? Still right answer to the wrong question, Jane. I said how many refused to respond, no, how many were over 59? And that's not just 49, it's what? Total? Yeah, 202 plus 49. Because what the question I asked was the total number who were 60 and over. That's 251. You're still reading the question, but I'm working my way up to the question. Why can I not just add this 156 and that 281 and then divide that by 1205? Why would that not give me the right answer? Because these 49 got counted twice. They were counted in this row and they were counted in this column. So either I can add these two numbers. I need to be pointing here so it shows up on the video. I keep forgetting because I like to walk. I can either add those two numbers and subtract off the 49 who were counted twice, or I can just take this 156 and add the 202 to it. And that way I wouldn't be counting the 49 twice. So I'm just going to say 156 plus 202 over 1205 would be 358 over 1205. It's going to be darn close to 25%. Somebody give it to me to 3 decimal places. 0.297? Do I have a second? Okay, 0.297. And that's all of 4.3. 4.2 was just understanding the basics of probability. 4.3 is using the addition rule to find the probability of A or B. And the main concept is don't count anybody twice and you'll be okay. Now we're ready for 4.4, which is not the probability of A or B, but the probability of A and B both happening on two different trials. Now, a minute ago, I said the probability of a die landing on 1 is 1/6. The probability of a die landing on 6 is 1/6. So the probability that a die lands on a 1 or a 6 is what? 2/6. You added, and then, of course, you could reduce. What about this? If you're going to roll the die twice, what's the probability that you land on a 1 the first time and land on a 6 the second time? Anybody want to take a wild guess? 1 out of 36. Multiply those two probabilities. All right, so when you're looking for probability of A or B, you add. When you look for probability of A and B, you multiply. The basic multiplication rule is used for finding the probability of A and B, and that means that A occurs in the first trial and B occurs in the second trial. The kicker is the second paragraph. If the outcome of event A somehow affects the probability of B, then you have to take that into account and adjust the probability accordingly. I'll tell you how in just a minute. But in my example of rolling a die, does landing on a 1, your first roll, in any way affect whether or not you're going to land on a 6 the second roll? No, they're completely independent of each other. Well, that's actually the next definition. Two events are called independent if the occurrence of one does not affect the probability of the occurrence of the other, and they're not independent if if one happening does affect the probability of the other happening. Now, I'm getting just a couple of slides ahead of myself when I tell you this, but think about sampling without replacement. If you had 10 marbles in a bag, 4 of them were blue, then the probability that you reach in and randomly grab a blue one is 4 out of 10, right? On your second, if you don't put that blue one back in, what's the probability of the next one being blue? Not 4 out of 10 anymore, but what? 3 out of 9. So if those two events are not dependent, and you would have to take that into, I said the wrong thing, not independent. They're not independent. They are dependent. You have to take that into account when you're calculating the probability. Dependent is the probability of one does affect the probability of the other, but that doesn't mean one is causing the other. The fact that you pull the blue marble out first is not going to cause you in any way to pull a blue marble out second, or not pull out a blue marble second. Classify as independent or dependent. Now, when we were looking at classify as joint or disjoint, we were saying on one trial, can both of these things happen? If not, then they were disjoint, and if so, then they were not disjoint. Here we're talking about two trials. Can these two, the one happening affect the probability of the other happening? If you go out to the driveway in the morning, turn the key, and your radio doesn't come on, what's your first thought? My first thought would be, oh no, especially if I know I had the radio on when I turned the key off. I'm thinking, oh no, my battery's dead. And I bet my lights aren't going to work either. As a matter of fact, I bet the whole car's not going to crank. These share a common power source. So this radio not coming on affects what I expect to happen with the headlights. Now, it's possible that the radio's just broken, but it does change the probability or your expectations about whether or not the headlights work because they share a common power source. So is that independent or dependent? Dependent. Now, that doesn't mean that your radio not coming on is going to cause your headlights not to come on. Just one happening makes you think, oh no, about the other. Number two, if you find out that your cell phone doesn't work, then you go, oh no, my car's probably not going to start. Not unless you believe in Murphy's Law. Murphy's Law is just everything that can possibly go wrong will. But aside from that, no, whether or not your cell phone works doesn't cause you to think anything about your car. So are those two events dependent or independent? Independent. Randomly selecting a consumer who owns a computer and randomly selecting a consumer who uses the internet. If you're doing a phone survey and you call somebody and say, hey, do you have a computer? And they say no. Does that affect the probability of whether or not they use the internet? Yeah, if you don't have a computer, yeah, you can go to the library, but it's also, it's less possible that you use the internet if you don't have a computer at home. So these two events are what? Dependent. Sampling without replacement leads to dependent events. For example, if you have 100 marbles in the bag, 40 red and 60 blue, the first marble you pull out has a 60% chance of being blue. Or you would say the probability of pulling out a blue marble is 0.6 if you wrote it as a decimal. If it is blue and I don't put it back in the bag and reach back in the bag and pull out a second marble, well, now there are only 59 blue marbles left out of 99 blue marbles total. So the probability that the next one is blue is just a little bit smaller. Every time I take a blue marble out of the bag, it reduces the probability that the next marble is going to be blue because there are less blue marbles. I'm taking them out of the bag and not putting them back. Each blue marble you pull out lowers the probability of the next marble being blue. That's what I mean when I say take into consideration if what happens on the first trial is somehow affecting what happens on the second trial. But then there's the 5% Cumberland, or 5% guideline for cumbersome calculations. I just need to slow down. This is something that you might not do in engineering or physics or chemistry, but you can do in statistics. If something is going to be very difficult to compute, like typing in the fractions 60 over 100 times 59 over 99 times 58 over 98 times 57 over 97, if I was going to draw out 10 marbles and I had to multiply those 10 fractions, would you agree that would be cumbersome? Yeah, I would call that cumbersome. As long as your sample is less than 5% of the population, as long as you're taking a small sample from a big population, then you can play like the events are independent and it's really not going to affect your calculation much. So you could play like you're putting the blue marble back and the probabilities just staying the same. You can only use that play like, that pretend that they are independent if your sample size is less than 5% of your population. For example, if there are 150 chocolate chip cookies and 100 Oreo cookies in a jar, and you randomly pull out 8 cookies from the jar, what's the probability that you get all Oreos? Well, what's the probability that the first cookie is an Oreo? Oreo. No. 100 out of 250. 100 out of 250 would be the probability that the first Oreo, the first cookie I draw out is an Oreo. And if I don't put that one back, the next draw, there are only 99 Oreos out of 249 cookies. And the next draw, there are only 98 Oreos out of 248 cookies. Multiplying these 8 fractions would be cumbersome. Especially if I didn't have a calculator, it'd be horrendous. Yes, and I corrected it. Yes, I corrected it. Make sure this is what your paper said. If you printed it this semester, it's correct. Last semester, I had a mistake there. So let's see if we can use the 5% guideline. Let's see if we can play like the events are independent. Well, I can only do that if my sample size is less than 5% of the population. What's my sample size here? I'm drawing out 8 cookies out of how many? Out of 250? How would I find out what percent that is? 8 out of 250. Just divide. 8 divided by 250. I thought I had it. 0.032. No, 8 divided by 250. That's 0.032. What is that as a percent? I just say change 0.032 to a percent. It's 3.2. That's less than 5%, isn't it? It's as long as it's less than 5%, I can play like those events are independent. And instead of multiplying these 8 fractions, I'm going to say, let's play like I'm putting the Oreo back every time. The probability is going to stay 100 out of 250 every time. Well, this wouldn't be any easier to punch on the calculator than this is, because you're still multiplying 8 fractions, except for you have a exponent button. That exponent button makes it much easier to punch this than to punch that. All right, so let me make sure you know how you're going to enter that. Well, actually, I typed it. On the calculator, you have to have that 2/5. I could have put in the 100 over 250, but since I could reduce it in my head, I did. Wouldn't affect the answer. I reduced that to 2/5. You have to have the 2/5 in parentheses, and then look for that caret button, that up arrow on your calculator. I call that your to the button. It's your exponent button. So 2/5 to the 8th. Somebody tell me what you get for that, and give me 3 decimal places. Okay, I have an excellent question. If a question in the homework is, what's the probability of blah, 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 could the answer possibly be 6 point something? No, and why not? No, that's not it. It's not between 0 and 1. If the question is, what's the probability, the answer has to be between 0 and 1. So did you punch that wrong, or is there something at the end of that answer that you're not noticing? Ooh, that's when you have to look. Hey, first you have to recognize that can't be right, and then look at the calculator again and go, ooh, there's that E. And that E means this number's in scientific notation. It's e to the negative what? -4, which means do what? 4 places to the left. And then if you round that to 3 decimal places, what's that answer? Would it round to 0.007? Let me punch it real quickly. I want to look at this. Because some folks don't have their calculators with them and they're frowning at me. 2/5 in parentheses is 2 divided by 5 to the 8th power is 6.5536 e -4. Move that decimal place to the left 4 places and then round to 3 places. And this 5 would cause that 6 to round up to 7.007. All right, that's what you should have for the probability that all 8 cookies you draw out are Oreos. Now, Does that number disappoint you if your favorite cookie in the whole world is an Oreo? What's the probability that you're going to get 8 Oreos out of that jar? Very, very low, 0.007. You're probably going to have to eat a few chocolate chips before you get 8 Oreos. Not that that's entirely a bad thing. All right. If two events are dependent, then the probability of A occurring affects the probability that B will occur. You have to take that into consideration in getting the 2 or more fractions that you're going to multiply together. Now you have some new notation here. This vertical line, you read that the probability of B, given that vertical line is given that A has already happened. For example, the probability that the second marble is going to be blue, given that I've already taken 1 blue marble out of the bag. So the formal multiplication rule says if you want the probability of A and B, you find the probabilities independently of each other and then multiply them together. Just multiply them together instead of add them. But if A and B are dependent, then this vertical bar, I don't know why these 2 vertical bars got scooched in the wrong place. They're supposed to be here and here. Just put those vertical lines in on your notes. For the second probability, you have to take into account what happened on the first trial. That's the big scary way of just saying, make sure you're checking to see that what happened on the first trial what happened on the first trial affects what's going to happen on the second trial. Sometimes it doesn't affect them at all, and those events are independent. But if they are dependent, you have to take that into consideration. The intuitive multiplication rule says the very same thing, just in words instead of symbols. All right, so let's practice finding whether 2 events are independent and then find the probability of A and B. That's the probability that both things happen. A happens on the first trial, B happens on the second trial. Now, try to picture what's going on. I have a calendar in number 1. I have a calendar. I'm going to rip a page out. What's the probability that if I just close my eyes and rip out a page, what's the probability that the page I just happened to get is July? Yeah, disregard all the extraneous pages in the calendar. 12 months, only one of them is July. So the probability that you randomly pick out July is 1 out of 12. Let me see where I can write that down. Probability of July is 1 out of 12. Now I'm going to close my eyes again, rip out another page, and see if it's November. Would those 2 events be dependent or independent? Tell me why you're saying dependent. You've already ripped out a page. There are no longer 12 pages in the calendar. So if you've already ripped out 1 page, that's the probability of November. Given that you've already ripped out July, the calendar started with how many pages? 12, and after you ripped out 1, it had 11. So what's the probability you're going to get November on your second rip? 1 out of 11. Because those 2 events are dependent, that's why the probability in the B part is not the same thing as the probability in the A part. now that I have calculated these two probabilities separately, how do I find the probability of A and B? You multiply them. If it was A or B, you'd add them. But since it's A and B, it's 1 over 12 times 1 over 11, or 1 over 132. Wouldn't be very often if you had 1,000,000 calendars and you closed your eyes and ripped out 2 pages, it wouldn't be very frequently that the first one just happened to be July and the second one just happened to be November. What is that probability if you round it to 3 decimals for me? No. That wouldn't be 0.132 unless you were 0.008. You actually have to divide. What you're thinking is if you had 132 divided by 1,000, it would be 0.132. And that's not what this is. This is 1 divided by 132. Anybody second that? Okay. All right. Thank you. What about number 2? If event A is, it's a girl, does that affect at all what you expect to be the gender of the second child? No. Those 2 events are independent. The first kid, the probability of a girl is what? You could say 0.5 or a half, whichever is your favorite. And then the probability of the second child being a girl, given that the first child was a girl, is what? Still a half. Because those 2 events are independent of each other. So how do you find the probability of the first child being a girl and the second child being a girl? 1/2 times 1/2. That means if you looked at 1,000 families that had 2 children, about 25% of them, both kids would be girls. What about my case? I have 3 daughters. If I looked at all the 3 children families in the U.S., what's the probability that if I randomly selected one of those, they would all 3 be girls? How would I get that probability? I think you know what? I don't know the decimal in my head, but I can tell you the fraction very quickly. Well, if I just had 1 more child, what would I just multiply by 1 more half? The probability of the third child would also be a half, and a half times a half times a half is an eighth. That's actually 0.125 or 12.5% of 3 children families would have all girls. All right. Finish that. What about the lottery? The lottery, I'm gonna be the lovely lottery lady, and I'm gonna draw ping pong balls out of, this is a 4-digit lottery, so I've got 4 buckets, 4 rotating things. I can't think of bins, 4 rotating bins, and I'm gonna draw a number out of each one. Well, the first bin has the number 0 through 9. Second bin has 0 through 9. So do the third and fourth. How many numbers are in each bin? 10, because don't forget 0. There are 10 numbers in each bin. This is not worded as simply as it could be, but let me just simplify it for you. Does what I draw on the second draw in any way depend on what I pulled out of the first bucket? No. They're definitely independent. What is the probability that that first ping pong ball is going to match the number on my lotto ticket? 1 out of 10. There are 10 balls in the first bin. I'm going to draw out one of them. Only one of them's a winner. So the probability that the first, I'm just going to say first number is a winner, because that's the shortcut way of saying all the stuff that's typed. Probability that the first one is a winner is 1 out of 10. What's the probability that the second digit is a winner? Because that doesn't depend on what I drew out of the first bucket. It's still 1 out of 10. So what is the probability that 1 wins and 2 wins? I'm not stating exactly what I mean just because it saves me a minute writing, and minutes are important right now. Seconds are important. Multiply them, because it's first and second are both correct. Let's say that we have 100 people gathered together in a gymnasium to watch a drawing for a $10 million prize. 100 people went in together, bought the ticket. They're all glued to the TV at the same time. After the first number is pulled, how many of them go, woohoo? One out of 10. So if there are 100 in the room, how many people say, woohoo? 10. How many people walk away? The other 90. All right, now there are only 10 people in the room. When the second number is drawn out, how many people say, woohoo? Yeah, there are only 10 people in the room, so only one is excited at that point. The other 9 walk away. This would be bad if it was a pick 4 lottery, because we still have 2 more ping pong balls to go. Just to show you why it's so hard to win the lottery, let's do the probability of all 4 numbers being correct, or being the winning number. How would you get that? There would have had to have been 10,000 people go in on a ticket for any of them to have a realistic chance of winning. And if you want to split, I'd split $10 million with 10,000 people. That would still make me happy. But unfortunately, I don't think I have 10,000 friends. I'd have to start a Facebook. And I'm not going to. Unless my grandchildren someday will not communicate with me any other way, I'm never going to have a Facebook. All right. Any questions on that one? Okie doke. Next. We're making much better time than my Monday, Wednesday class when we did this. We didn't get through all of our examples in that one. Number 4, very, very real life. In industry, quality control is important. If you don't make a quality product, you are going to go out of business. Now, if you're making, let's say, bolts that hold really important things together, bridges maybe, you probably make 10,000 bolts a day. And that bolt has to be the exact size or pretty darn close to it to keep that bridge standing. It's not okay to have a too big bolt. You're going to have to throw them all in the river, and then you're going to get fired for wasting money and polluting the river too. They can't be too small or it won't fit snugly in the hole it's supposed to fit in. But you're making 10,000 bolts a day. Can you check all 10,000 bolts with those little calipers that measure the diameter? No. You'd have to hire 5 more people just to measure all the bolts. So you take a sample. You look in the bucket of 10,000 bolts, you reach in and you grab out 4. And you say, if these 4 are okay, I'm going to assume today's batch is okay. If all 4 are good, I'm going to say, yep, today's batch is off for shipment. If one of those 4 is bad, then I'm going to say chunk today's. Or maybe let's go back and test each one. I'm going to have to do something though. All right, so that's called batch testing. The entire batch is accepted if every item in the sample is okay. Now, here we're talking about airport baggage scales. We know that out of 810, 102 are defective. We want to find the probability that if we reach in, grab 4 of those scales, what's the probability that we're going to accept the whole batch? Just looking at these numbers, do you think we should accept the whole batch? That's about 12% of them bad. Would my sample of size 4 catch that? That's the question. And rather than just saying my gut says no or my gut says yes, let's find the probability that if we reach in and grab 4, none of them are going to be bad. That's what we're looking for. Let's see. If 4 of the scales are randomly selected and tested, what's the probability that the entire batch will be accepted? Tell me how to calculate the probability that the first one I draw out is going to be good. No? What's the probability that the first scale I test is going to be fine? 1. No, there are more than just one bad one in the batch. That would give me the probability that I find a bad one, but I ask for the probability that I find a good one. You see how important it's going to be to read carefully here? If I ask for a probability that one is accepted and you say 102 divided by 810, you got the right answer to the wrong question. You just told me what's the probability that one is bad. So how are you going to get the probability that one is good? That would give you the number of good ones. 102 defective means there are 708 acceptable. And so the probability that the first, I'm just going to say probability of acceptable, if you're writing with a pencil, put a big old 4 on that thing I scratched out. That's what we're actually trying to find, not just the probability that the first is acceptable, but the probability that all 4 are acceptable. Well, in a long conversation, we just figured out that the probability that the first is acceptable is 708 out of 810. That's a pretty high probability that the first one's going to be good. If we don't put that one back in, if we draw out an acceptable and don't put it back in, what's the probability that the next one's going to be acceptable? 707 out of, now there are only 809. And if that one's acceptable and I don't put it back, what's the probability that the next one is acceptable? And the last one? Probability that the last one's acceptable? Yes. Would you call multiplying those four numbers cumbersome? It's kind of there's a fine line on what's cumbersome and what's not cumbersome. I can't give you a magic rule on that. I promise that I'll try to make the one on the test obviously cumbersome or obviously not cumbersome. That looks pretty cumbersome to me. It's not hard to multiply two fractions, maybe not even three fractions, but four is getting on my nerves. So what could we do to use the 5% guideline? First thing I'd have to check is 8 less than, not 8, I'm not drawing 8, I'm drawing 4. Something's going on with my 4s. Is 4 less than 5% of the 810? Is it? Yeah, it's way less. And because it's way less, I can say the probability of 4 acceptable what does the 5% rule say that I can do? No. The 5% guideline says, well, just play like you're putting it back. And that way, all 4 draws, the probability of acceptable would be what? What was it originally? 708 over 810. If you use the 5% guideline, you just multiply that times itself 4 times, or even easier on the calculator, 708 divided by 810 to the 4th power. That's much easier to enter on the calculator. But you do have to have this fraction in parentheses before you raise it to the 4th power. Somebody have that for me? 0.584? Anybody second that? A third? Okay, I got several nods. 0.584. That means if I use this method, if I only use a sample size of 4, 58, almost 60% of the time, I'm going to say, yep, today's batch is good. I only drew out 4. All 4 were good. Yep, today's batch is good. But we know today's batch is not really that great. So that tells me I'm going to need to draw out more than 4. Maybe if I drew out 8 and all 8 were good, maybe that would be sufficient. But this pick 4 method is not going to catch how many days we really have an unacceptable number of defective scales. So I would say answer to that second question is no.